So your chapter 4 homework's up there. Most of it is fairly straightforward. It's just identifying bond angles, hybridization, bond overlap, that kind of fun stuff. Okay, and then a lot of cis-trans things. So we looked at the nomenclature. So we've got our alkyne nomenclature, and then our alkynes as well. So I just included that in there. I didn't really want to talk about it again. Anybody have any questions about those that I need to go back over? Okay, I'm happy with that. The cis-trans naming, okay, dealing with that. So whenever we've got a double bond, we have to also add a second tier as far as the nomenclature goes. We have to watch out for cis and trans isomers. Okay? So if your structure has the possibility to have a cis-trans conformation, you must specify that in the name. Okay? If you don't, it is technically wrong. Okay? So make sure you get that extra addition in there. It's just like RNS as far as that goes. You've got to make sure you go through and assign it. Okay? I don't think any of these examples are new, but let's go ahead and do a couple of them anyway, just for practice sake. So if we go through and evaluate, let's say this one right here. Okay, so to go through and process, what? Draw. No, I just got the wrong screen. Draw, I say, see? Now it's there. Okay, so to go through and evaluate these structures, we've got a series of rules that can help us propagate these things. I do want to mention that when it comes to the rules, we can't apply rules to everything in organic chemistry. Okay, so you can't follow or find an individual stepwise thing for all things that we're going to do. Okay, it works really well for nomenclature and anything related to nomenclature because those are rule-based things. Okay, I'll try and simplify and make as many individual steps as possible so that you can apply those steps to every problem. But in a lot of cases, it's not clearly defined what steps you should be approaching. Okay? So, as far as determining cis and trans for this structure, we'll cut the double bond perpendicular in half. Okay? So what we'll go through and do is put in our half, okay, perpendicular. And what we're going to do is look at each half of that and determine if there's priority. Okay? We'll star our highest priority atom. So what we'll do is look at the atoms attached to the double bond. This carbon is part of the double bond, so we want to look for the things attached to it. Okay, so we've got an atom over here. What atom is that in red? Carbon. It's a carbon. Okay, that's the only thing I see attached to our double bond. Is there something else there? There's an implied hydrogen coming off there as well. Okay, I've noticed some people draw it slightly differently. And unfortunately, in this case, you must draw it the way I just did it. If you go through and say, okay, well, I'm going to draw on my other hydrogen here, okay, there's a couple reasons why that is bad. The primary reason, what's the bond angle around, or what's the hybridization of this carbon? sp2, which means what bond angle? 120 degrees. We need to show that 120 degree angle as best as possible when we draw our structure. What bond angle looks like is happening between our double bond and that hydrogen? Certainly not 120 degrees. Okay? So when you're going to try and assign cis and trans, make sure that you put that in there as appropriately or as close as you can to the actual shape, which would mean putting it out here. Okay? We're now going to compare hydrogen to carbon, the atom immediately bound. Is there a difference in atomic weight? Or atomic number, sorry. Yes, which one has the higher atomic number? Carbon, so we will star the carbon. Okay, we'll now move to the other side. We move to the other side. There's our double bond carbon. We want to know what things are attached to it. Okay, let me color that in black. We want to know what things are attached to that double bond carbon. What do we have? Got a carbon up here. Where's that hydrogen? It's going to come down over here. We'll now compare hydrogen to carbon. Is there a difference in atomic number? Yes. Which one has the higher atomic number? Carbon. We'll star that. Step 2 is to cut the double bond in half, now parallel to the double bond. Okay, by parallel, we're now going to go, see if I can do this, right through the middle here. Where are our stars with respect to that second cut? They're on opposite sides of that line. The conclusion of opposite we come up with is trans. Okay? If we were forced to assign E and Z nomenclature to that, okay, we could then also call it E, or an E double bond, as opposed to referring to it as trans. Both of those definitions, or both of those terms, would be appropriate. Okay? Let's move to another example. Let's take a look at the one down here now. And I'm going to cut in half this double bond. Okay. We go through and evaluate each half. Bromine versus carbon. Which one has the higher atomic number? Bromine. We can star that. We move over to the other side. Carbon versus carbon. Difference in atomic weight or atomic mass, atomic number. No, so then we'd have to track out until we found a difference. What we'll end up finding out is that this top one is starred. Dang it. Change my mind. I don't want to do that one. Let's do the other double bond. We already have a trans. So let's go look at this double bond. Let's cut that one in half. We go through and evaluate our differences. One side of the double bond, we've got hydrogen versus carbon. Which one has a higher atomic number? Our carbon. We can star. Go to the other side. Hydrogen versus carbon. Carbon, we star. Cut our double bond in half. Now parallel to the bond. Where are our stars? Same side of that line. We'll refer to it as cis or Z. Okay? In this case, okay, the one down here, this example, we're going to have to refer to it as Z and not cis. Why? There's two double bonds. So if we said cis, we don't necessarily know which one we're referring to. And if we did the cis-trans nomenclature in front of that name, we'd end up making the name really, really, really long with a whole bunch of cis's and trans. Okay? So that's why we'll stick with the E and Z nomenclature when it comes to that one. Okay? Kind of makes sense?
So you only use E and Z if there's more than one double bond?
Or if you're looking at a structure that has more than more than two different things on it.
Okay.
Yeah. Cis and trans officially really only applies to, I guess I don't have that rule on here, do I? No. If it has two hydrogens attached to the double bond. That's the only time cis and trans really apply. So you're looking at two non-hydrogen groups. Okay? E and Z is where we're strictly looking at, or the most accurate definition. So cis and trans is just kind of fast. E and Z is official. Okay? It's like a nickname.
So would you put E and Z in that name?
You would have to specify E and Z. Yep. And making sure to tie the E and Z appropriately to each double bond. How would you tie them? Wherever you're numbering that double bond. We name it. Let's go through and try and name it.
I was going to say, does one come before the other when it comes to E and Z, or would you
So
still go by
let's
the name?
go through and name this compound down at the bottom here. What color do I have here? Okay, so let's go through and name that. First thing we got to do is number our carbon chain, or figure out our longest carbon chain that contains the double bonds, which means we're going to be looking there. Okay? So that has what? 1, 2, 3, 4, 5, 6 carbons. So we'd be looking at hex. Okay. We've got double bonds, so we'd be looking at an ending of -ene, except there's 2 double bonds, so we'll have to specify those. That will be hex, whoops. Could just call that an A. We end up with, I believe I'm doing this one right. Hex, no, I don't think we want the A. Hexdiene, so 2 double bonds. Where are those double bonds now? Now we have to go through and number. We've got 2 options. We can start our 1 over on the right-hand side and move, was that right to left? Or we could start our 1 over here and go left to right. Which one's the appropriate way to number?
Right, the one on the right first.
We're going to go right to left. Why? Because our bromine substituent would show up earlier in that case. Our first substituent gets a lower number. Okay? So if we went through and numbered, we've got 1, 2, let's do a different color. 1, 2, 3, 4, 5, 6. Our first double bond shows up at position 2. Where's our second double bond show up at? Position 4. So we get 2, 4 hexdiene. Do we have any substituents on the ring? Okay, we've got our bromo, which I already circled, and then we also have this piece. So we could go through and name each of those pieces. So this is our bromo. This piece here has 2 carbons, so we're looking at an ethyl. Where's the bromo show up? Position 2. Where's the ethyl show up? Position 3. If we were going to put our name together officially appropriately, how are we going to start this? We'll do the bromo first. Ooh, this is going to be backwards. Let's see if I can fit it. 2 bromo, 2 ethyl, 2,4 hexdiene. Whoops, sorry. Yep, I even had it 3 down there. Okay. So 2 bromo, 3 ethyl, 2,4 hexdiene. We now need to specify cis and trans on our double bonds. Okay. Except because we have multiple double bonds and more than just or less than just 2 hydrogens. Okay. We have to use the E and Z nomenclature. For this double bond, what did we decide it was?
Z.
Z, because they're on the same side. Be like an idiot. At least it matches the way I look, right? So we could go through with the second double bond. Our second double bond is, what did we decide? E for our second double bond. Okay. So we're looking at Z and E. Our E double bond showed up at what position? 2. So at the front we would say 2 E, and then 4 Z, 2 bromo, 3 ethyl, 2,4 hexdiene.
You put them in parentheses?
Yeah. Those of you attending lab, I'm going to make fun of biochemistry naming in lab today. Because if you think this is gross, you should see what biochemistry does. Okay? Thankfully, you don't have to name things in biochemistry. You just have to know what the name is. So, okay? Questions about our cis and trans, E and Z, all that fun stuff. Okay? So we can go ahead and move on. This pen is falling apart. One thing that I forgot to mention and look at was kind of comparing our alkanes versus our alkenes. So we're going to do this comparison a couple times, maybe even a couple times in this lecture. So let's go through and look at molecular formulas for each of these compounds. Okay, so if we take a look at our upper left-hand corner, how would you name that compound? How many carbons are there? 1, so we'd be looking at meth. Do we have anything other than single bonds? Nope. So we have methane. What's our molecular formula? We got CH4. If we move to the next one, what do we have? Name. We've got ethane because we've got 2 carbons now. And our formula is C2H6. Last one in that column. We get propane and we get C3H8. So one of the things that you might have seen in the in the textbook, although I don't think I directly stated it in class yet, is that we can start to notice a pattern for your alkanes. Okay? If we went through and said we had a general formula, carbons, and we had n carbons, so some number of carbons, how many hydrogens would we have? Okay, so we could try 2n, see what happens in that case. So in our methane structure, what's n? 1. If our formula was correct, nope, doesn't work. If n was just equal to 1, we would say there's only 2 hydrogens. What's our formula say? 4 hydrogens, so that didn't work. Okay, so how could we adjust our formula now to account for those 2 missing hydrogens? How about +2? And if we go through and check our formula now in comparison to all the others. In ethane, how many carbons are there? 2. 2 times 2 is 4 plus 2 is 6. Does that match our formula for ethane? Yes. How about for propane? What's n equal to? 3. 2 times 3? 6 plus 2, 8. Does that match our formula? Yes. So this is a standard formula for alkanes. Okay? If we don't have any double bonds or anything else messing with us, that formula is going to hold true. Okay, regardless of the rest of our structure. Okay, so that's kind of nice. What happens when we move to alkenes? Okay, so let's take a look at the first alkene there. What's the name of that one? Except a couple names on this one. Ooh, come back here. We get ethene. What's the other name we might see? The common name. The ene is our most important thing. What's our functional group in that case? What's the piece? Ethylene. Okay, so you could see ethylene referred to in that case. I would expect ethene from you guys. Okay, what's our formula? C2H4. What's happening for this one? What's the name of that one? We've got propene, or propylene. Also works as the common name. What's our formula there? C3H6. Okay, what would this one be? Last one. Diprop. There's 2 propes in there? Propediene. Help, I'm dying. Is this mic on? What's our formula? Sorry, yeah. We get C3H4. So what's happening is we change the hybridization in our carbons. If we move from ethane to ethene, what did we lose? 2 hydrogens. When we move from propane to propene, what did we lose? 2 hydrogens again. Okay. What did we gain in that transition? Ethane to ethene, what did we get? Double bond. What did we get when we moved from propane to propene? Double bond. How many hydrogens did we lose when we moved from propane to propdiene? 4 hydrogens, and what did we gain? 2 double bonds. So we can start to notice that there's a pattern here. Okay, if we lose or get rid of 2 hydrogens, we get 1 double bond. Okay, so what, and you may have seen this in nutrition, we can look at degrees of unsaturation. And it's related back to numbers of hydrogens being removed and your double bonds. Okay, so we can look at 2 versions for our alkyl functional groups. If we have a saturated alkane or saturated hydrocarbons, so just hydrogens and carbons, all our carbons are going to be signally bonded, and in this case we're looking to hydrogens. We're also going to add no rings. We'll come back to the no rings in a second. And we end up with the formula CnH2n plus 2, okay, which we just talked about. If we're unsaturated, what we've done is we've removed hydrogens. We've unsaturated our structure. So the saturation is looking at how many hydrogens we've pumped into it. In a saturated structure, I've fully filled it with as many hydrogens as I can get into it. In an unsaturated structure, I've pulled some of those hydrogens out. It's no longer saturated with hydrogens. Okay? To do that, we'll see a couple different functional groups show up. Anytime we see a double bond, triple bond, or even cyclic structures. What's the relationship between a double bond and a triple bond? More than one bond. What's that extra bond that's being added there? No, what type of bond? A pi bond. So when we add a pi bond, that's where we're getting our degrees of unsaturation. Okay, so your enes, ynes, and your not quite cyclostructures, like I said, we'll come back to those, are where we're looking at removing hydrogens. Okay, and if we go through and now look at a formula for this, our formula becomes a lot more complex. Okay, and I don't want you to get too bogged down in this formula. We'll look at a couple examples that show this. Okay, as we add a double bond, we lose 2 hydrogens, right? So our formula, if we were looking at our CnH2n plus 2 from our alkane, if we add a double bond, just one double bond, we have to get rid of 2 hydrogens. So we lose 2 hydrogens from our structure. I don't think this formula quite works. Okay? We'll come back to that in a second. I just kind of wung it real quickly. Okay? So as we pull 2 hydrogens off, we end up adding a double bond. What?
Is that the past tense of wing is long?
Yeah.
Wing is long.
You didn't know that? I'm sure it shows up in the dictionary. Okay? So what we're looking at is adding double bonds to our structure, and that's accounting for our unsaturation. We can go through and classify degrees of unsaturation as a way of representing how many double bonds showed up in our structure. Okay? Those of you that may have been in dietetics programs, okay, where might you have seen degrees of unsaturation before? Saturated fats and unsaturated fats. What are they referring to?
Deliciousness.
The amount of double bonds. They're all pretty much tasting the same, actually, with this. It's the amount of double bonds within each of those structures. Okay? That's all they're ultimately looking at. And when you change the number of double bonds, it changes the physical properties of that structure or that compound, and you end up with either oils or liquids or fats where they're solids. Okay? And it's all coming back to this simple concept of double bonds versus no double bonds. Okay? So let's look at some problems that we could play around with here. So if I gave you propane. So we draw out propane here. We got 3 carbons. All our hydrogens on this. How many degrees of unsaturation are in this? 0. How do you know there's 0? There's no double bonds. Good. We're paying attention. I like it. So now I spent all the time to draw that. Let's erase it. Let's draw the next one. Propene. How many degrees of unsaturation are in this one? You talk faster than I can write. Yeah, we've got 1 degree of unsaturation. Why? There's a double bond. What happens if we look at our propdiene? How many degrees of unsaturation do we have now? 2, because we have 2 pi bonds. What happens if we look at propine? How many degrees of unsaturation do we have here?
2.
It's 2. We're looking not at double bonds, but at the number of pi bonds. How many pi bonds are in a triple bond? We get 2. And then we have the sigma bond running in between. Okay? Let's take a look at our cyclic structures. So here's where our definition kind of gets a bit wonky. So let's take a look at, yes,
How many degrees of saturation did you say that was?
the propine, 2 degrees of unsaturation because there were 2 pi bonds. Okay, let's take a look at a cyclic structure. We'll look, for the sake of my drawing abilities, we'll look at this one. What's the name of this compound? Cyclobutane. So the cyclo because it's a cyclic structure, and the bute because we got 4 carbons. How many degrees of unsaturation do we have in this one? No double bond, so we would assume 0, right? Well, what's our formula? C4H8. So we just decided that it was a saturated structure. So let's match our saturated formula to that formula. So what is N? 4. What is 2 times N? 8 plus 2 says 10 hydrogens. So for that formula, for 4 carbons to be a saturated alkane, how many hydrogens do we have to have? 10. Do we have 10? No. So your degrees of unsaturation not only account for the presence of pi bonds, but also rings. Okay? So it's not just pi bonds, but also rings that you have to be concerned about when determining degrees of unsaturation.
So then what would that be?
Huh?
What would that be?
So how many degrees of unsaturation does this structure have? Okay? So if we go through and look at this, how many hydrogens have we lost from our fully saturated structure? So if it was saturated, we had C4H, 2 times 4 was 8 plus 2, 10. We're looking at a saturated structure versus our compound. So what we're going to do is try and come up with a comparison between these. I'm going to have to erase this so I can draw. This eraser sucks. Erase faster. I'll say that's good enough. Okay, so let's take a look at a comparison here. We've got 10 hydrogens in our saturated structure. Okay, we've lost some hydrogens, so we want to find out how many hydrogens we lost. How many did we lose? Yeah. That's not what I wanted to say. How many hydrogens do we have in our structure? 8. So if we do 10 minus 2, or 10 minus 8, we get 2 hydrogens lost. Okay, if we're figuring out our degrees of unsaturation, okay, our 1 degree of unsaturation was 1 pi bond. How many hydrogens did we lose when we made 1 pi bond? 2. How many degrees of unsaturation do we have? 1 degree of unsaturation. Okay, we're going to work a couple examples on this. Okay, so a ring counts as a degree of unsaturation. So let's go ahead and clear everything here now and kind of summarize. 1 degree of unsaturation, okay, equals 1 pi bond or 1 ring. Okay. 1 pyre. You guys can understand what that means, right? Okay. So let's go through and look at a couple examples. We looked at structures and we're able to figure it out with structures. Let's see what happens if we jump to formulas. So let's take a look at C3H6. We want to figure out how many degrees of unsaturation there were. So ultimately what we have to do is compare that back to what it would be if it was fully saturated. Okay? So if it was fully saturated, our saturated structure would be C3H. 2 times 3 is 6 plus 2 gives us 8. Thank you, Professor Count. Okay? To figure out our degrees of unsaturation, it's going to be our number of hydrogens and our saturated structure minus the number of hydrogens in the formula we're evaluating, which gives us the number of hydrogens that we've lost. But to get degrees, we have to realize that 1 degree equals a loss of 2 hydrogens. Divide by 2. Okay? So what do we get in this case? 2 over 2, which equals 1 degree of unsaturation. Two over 2 equals 1 degree of unsaturation. So let's see if that's actually true. Let's build a compound or a structure that matches this formula. So we'd have to get 3 carbons in there. We'd have to put in our 8 hydrogens. 1, 2, 3, 4, 5, 6. Oh, we were supposed to be C3H6. Sorry. Saturated, that was our saturated. Our formula was this. We were trying to figure out how many degrees of unsaturation it had, right? So we've accounted for now our 6 hydrogens. Okay. To polish off our octet, what do we need to add in here? A double bond. How many double bonds are in this structure? 1. 1 pi bond equals 1 degree of unsaturation. What did our calculation tell us we had for degrees of unsaturation? 1. Huh? As far as this calculation goes, it does not tell you if it's a ring or not. Okay? Is there something else? This is aimed for those of you in lab. Okay, so let's say, because we have an alternate structure that we could draw here, so in this case we did the double bond. We could have just as easily have drawn it as a ring. Okay, to match that same formula. We would have gotten this structure. So I'm drawing fast and terribly.
It doesn't have to be.
Thank you. Same deal, right? C3H6. How could we tell a difference quickly between these two structures, particularly in a lab environment? What's that? But you can't see that in a lab environment. You have 2 bottles. One of these is the cyclopropane. One of these is the propene. You could try a boiling point, but the boiling point's going to take a while to do. I heard someone else say the other option. We could add bromine to it. Bromine reacts with double bonds. So what happens? We add our red bromine solution. If it turns colorless, what does that tell us? We've got the presence of a double bond. There's our compound. Okay, and we're going to look at that bromine reactivity probably next week. I don't think we're going to get to it today. Okay? So let's look at other options. I want to know how many degrees of unsaturation there are for C6H6. Any guesses what that structure is? Nope. So we'll say that's a no. Nobody knows what that is. You'll become familiar with it when we move into Chapter 9. Okay, so let's go through and do our same ideas of trying to figure out our degrees of unsaturation. Okay, so the first thing we're going to have to do is figure out how many hydrogens should have been in our saturated formula. If it's saturated, go with a different color here. So if it was saturated, we'd have C6H14. So to do our degrees of unsaturation, we'll take our 14 hydrogens minus the hydrogens from our actual formula, which will be 6. We'll divide by 2, because there's 2 hydrogens per degree of unsaturation. And what do we get? That's why I'm a chemist, not a mathematician. Okay, and we get 4 degrees of unsaturation. So let me draw a sample structure, and you can tell me if this is going to be correct. So if we did cyclohexane, be right. Is this cyclohexane? How many degrees of unsaturation are in this? So remember, what counts as a degree of unsaturation? Pi bonds and rings. How many pi bonds are in this structure? So we get 3 pi's. What else do we have? 1 ring. Total that up, what do we get? 4 degrees of unsaturation. Okay, so we end up finding our 4 degrees of unsaturation within a benzene ring. Kind of makes sense? Okay, questions about this? Should we do another one? Yeah, okay, let's pick a tricky one. Let's take a look at C10H24. Okay, if it's fully saturated, so our first step is to look at our fully saturated situation. Okay, fully saturated would say we have C10, N is now 10, okay, 10 times 2 plus 2, we get 22. Huh? 22 minus the number of hydrogens in our structure divided by 2 gives us -1. What does that mean? Our initial formula was wrong. That is not physically possible to put that many hydrogens around that structure. We cannot physically do it. 22 minus 24 is -2 over 2.
Oh, I'm like, where'd you get that?
I was going to write -0.5 if that made you feel better.
That's -2, that's not -1.
Okay?
Are you always going to start with unsaturated?
No, so what I'll do is give you a formula. You have to tell me if it's unsaturated or saturated. So I could give you a formula and say, first off, is this a reasonable formula? So you'd have to go through and find out you either have 0 or a positive number. If you've got a negative number, is that a possible structure? No. So right off the bat, you could stop working. You got a negative number? No. You're being a jerk. Give me something I can work with.
Can we put a frowny face?
Sure.
I'll put frowny face if you put a frowny.
Okay. I don't even know where we're going. What are we talking about?
Saturated?
Saturated and unsaturated. So you would go through and find out, based on that formula, you would say, no, it's not possible because you got a negative degree of unsaturation, which isn't possible. Or you'd go through and find out that it's a non-negative number, so 0 or positive. So in that case, you'd say it is a possible structure, and then you'd tell me how many degrees of unsaturation there were. Okay? So when you run through the calculation, if you get 0, how many degrees of unsaturation are there? 0. How many pi bonds are there?
0.
How many rings are there? 0. There you go. What if you got 4? So in the C6H, let's go back and reevaluate this one. Our C6H6. Fully saturated says we have C6H14 to figure out our degrees of unsaturation. Ooh, that looks terrible. Let's zoom in a little bit. We got 14 minus our 6 from our actual structure divided by 2. We get 8 divided by 2, which equals 4 degrees of unsaturation. How many pi bonds are in your answer or in your structure? There could be 4. We don't know exactly how many pi bonds are in that structure. But there's no more than 4. Okay? So for your possible answers, you could say there are 4 pi bonds. Or there's 3 pi bonds in a ring. Or there's 2 pi bonds and 2 rings. If it's negative, it's not possible. If it's positive, you have to realize that you're going to look at some combination of rings and pi bonds. Okay? Does that make sense?
Would you accept any of those answers? Or
Yes.
all of them?
Depending on what I asked for. If I asked for all of the possible answers, you'd have to give me all possible answers. Probably would just ask for one. Okay? Questions about that? Okay, we will go ahead and move on. Very last part of chapter 4 looks at natural products and isoprene units in relationship to terpenes. Okay? I'm not going to talk about this a whole lot except to say that isoprene is the pretty much fundamental building block of most biological structures or most biological compounds. Okay? I don't know where that name came from except for the iso portion, which we've got out here. And then apparently this is a prene. Okay? So we've got 5 carbons in our building block. And what natural products will do is take that structure and start adding them together in such a fashion to build larger structures. So if we take a look at each of these compounds, this is where it's likely going to bite me. Okay, we could go through and identify how many different isoprene units were in each of these structures. Okay, so let's see which ones of these you guys are familiar with. Okay, because I know some of you are doing dietetics or biology, things like that. Any of those structures look familiar? Limonene, good call from the lab. I like that. I think that's right. Anything else? Can you see that answer? You want to know why you can see that answer? Retinol is what allows you to see. You're looking at conformational changes within that structure, and that's how we physically see things. Is that structure changing between cis and trans? When light hits that molecule, it changes conformations. We detect that conformational change as light. And that's what we actually see, is that structure changing its composition. And that's how we see things. Kind of crazy. At least I think it is. Okay, how about this top one? It's a hint, it's orange. It's beta carotene. Okay. Carrots are helpful because why? Why do we or what's the rumor behind why carrots are good? Because it gives you night vision. Why might that help you with night vision? Beta carotene look awfully similar to retinol. Okay, they're related to each other. Okay, what's that last one? Is that an answer? We've got cholesterol. Okay. Each of these compounds are different mixes of the isoprene unit. Okay. For those of you in the lab, we looked at how limonene was composed of different isoprene units. So to go through and identify these, we're going to try and find the easiest way to connect these. For me, personally, it's going to be identifying the iso functionality. Okay, so let's go to a different color here. We're looking at that group, which is now even messier. So if we go to limonene, where I think it's easier, and I'm probably not going to attempt the others because I think I'll fail. It's supposed to have 5 carbons in it. We've got 1, 2, 3, 4, There's our 5th carbon. So there's one isoprene unit. There's the other. Limonene has 2 isoprene units. Okay. If we tried to go through and do it for retinol, because that's at least a little bit easier, where do you think you'd start? Or where might be a nice way to start that one? In the ring. Where in the ring? That's where I would start, I think. So we got 3, 4 carbons, now 5. How many isoprenes do we have in there? 3, 4. Yep, you're right. We don't want to touch the stuff in between. You'll notice that I haven't highlighted that. So let's go through and highlight that in a different color so we can see it stand out. Why did I not highlight that as part of the isoprene unit? What is that area? It's a bond. It's not a carbon atom. It's a bond. Our carbon atoms are the points or the ends of those lines. If I decided to color that in, I'm now including an extra carbon because at the end of that line there's another carbon. Okay? Does it kind of make sense? So the idea is to be able to go through and appropriately identify those pieces. There's a few problems like it in your textbook. As far as your exam goes, I might ask one kind of thing like this. Okay? So you should be able to go through and highlight and identify those units. Okay? If for some reason you go through and you happen to go the wrong direction, what ends up happening? You get some weird odd number of carbons in there. What does that mean? You started in the wrong place, try again. Okay? Seeing a bunch, I don't think I would ever give you cholesterol, by the way, just so you know. Okay? But in theory, you should be able to go through and find the isoprene units within that, just like you did for the limonene and for the retinol. Okay? Textbook talks a whole lot more about how cool these things are and that kind of fun stuff, so you can read about that. Questions about any of that? Confident in counting those? Do I need to try and count beta-carotene or cholesterol? I don't really want to because I'm pretty sure it's going to be one of those fail attempts. I think I'm going to go through and not do it right. But if you want me to, I'll attempt. Thanks. Which one should I do? Beta-carotene, that's what I wanted to hear. I like that one. So we'll start up at the top. Okay. We've got our 3 carbons. We could go this direction with our next carbon. The problem, if we count that out, is then how do we get this carbon into an isoprene? We can't. So that means we went around the ring the wrong direction when we tried to highlight our isoprene unit. So let's go the other direction. So there's an isoprene. There's another one. There's another one. Hey, I got this one. I think I got this one. And now they're going to shift and go the other direction. This one. Okay. Oh, yeah, you're totally right.
Did I get this class? Yes.
Well, you don't get it, you got it right there. Okay? So the idea is trying to go through and identify those pieces. If you go the wrong direction, you end up leaving out a carbon. Try and go back and find out where to fix it. Okay? The more complex the structure, say something along the lines of cholesterol, you start to run into issues because biological molecules also tend to add in other things. You'll notice that I did not explain retinol, the alcohol, where that came from. Okay? I also didn't explain anything about the double bonds. Where are all those coming from? The isoprene unit is changing its functionality. We're the biological systems are changing the reactivity of that structure, allowing it to react more or differently, depending on the situation we're looking at. Okay? I believe ultimately, so I'm going to erase everything here. I'm pretty sure when it comes to the isoprene unit, we're actually looking at a double bond there and a double bond here. Those double bonds add the reactivity that we need to actually put these structures together. Okay? And we'll talk about some of that chemistry, but I doubt you'll see it in biochemistry, and I'm not going to go into it in gory detail in this class. Okay? Yes?
So on the test, you just want us to identify the isoprene?
Yes. Okay? So the possible questions that I would ask with the isoprene would be how many isoprene units are in this, or highlight the isoprene units. Okay? Or both. Why not? Okay? Questions about your isoprenes? Okay, what is a terpene? It's a chain of isoprenes. That's all it is. We just have multiple isoprenes in the same structure. That's the end of chapter 4. So now what we start doing is moving into the reactivity of alkenes. Okay? This is also where my slides are going to go into kind of a nosedive because I didn't have time to build a whole bunch of structures. So I'm going to be drawing things as we go through this. I'm going to try and keep them relatively simple, both so that I don't screw it up, and because we're low on time. I don't want to make it more complicated than we need to yet. Okay? What's that?
I mean, we can give you time. You can come back on Tuesday.
No, it's okay. I appreciate the offer. So what we're going to look at is our alkene reactivity. Let's see, did I get a slide in here? See, did I get any figures in there? I did. So let's go ahead and take a look at our alkanes and alkenes. Yes?
Christian, are you still going to be running the tally on homework?
Yes. All this homework has been posted and has been posted since the exam, since before the exam, to Canvas. I have noticed that Canvas is kind of not as nice as I would like it to be as far as prioritizing announcements. Okay? So I've been putting the homework into the same homework announcement. Because I made that announcement at the beginning of the semester, it's now at the bottom of the list. Even if I go back in and edit it, for some reason it likes to shuffle it to the end. It's not prioritizing it and bringing it up to the front. So when you check the announcements section of Canvas, what you want to do is check the bottom or one of the earlier announcements. Wherever it says the homework announcement, that's where you'll find all these problems. Okay? What? Yeah, sorry.
No, not you.
Okay, well that's good. So, we've looked at our structures now. We know how to name them. So now we've got to evaluate our chemistry. Okay, so let's go back. Just like we did with our alcohols and our amines, we're now going to evaluate those structures, see what changes about the structure, and how is that going to potentially change our reactivity. Okay, so everybody's favorite thing, we're going to go through and identify Bronsted-Lowry acids and bases, Lewis acids and bases, nucleophiles and electrophiles. Okay, so you need to be able to look at the structure and see that chemistry. So if we look at an ethane, the ANE ending tells us that we're looking at just singly bonded carbons. So we've got, in this case, C2H6. If we look at ethylene, decide to get mean and jump to the common name, we've got the ene ending for our double bond, the ethyl as our number of carbons. So we're looking at our 2 carbons with a double bond. Where should the double bond go? Only between the carbons. We don't have a choice. Okay? So, when we looked at ethane, we saw that before. What kind of chemistry do we get there? None. Why not? What are the bonds? Where are the electrons in that structure? They're covalent bonds. True. How else can you classify those bonds? Don't tell me single, but yes, you're right. They're nonpolar. Damn. Keep going. Yeah, there we go. Sigma. We're looking at sigma bonds, okay, in our alkane. Which means what about where the electrons are located? They're in between our atoms, so we're in the middle of the structure. Okay? If they're in the middle of the structure, what does that mean about their availability to react with anything? They're not available. So what do we predict for our reactivity? We get not reactive. Okay? What happens when we move to ethylene? So we still have nonpolar bonds. Okay? We still have covalent bonds. But we're now changing the type of bond in between those carbons. Not only do we have sigma bonds, but we have a pi bond. What's different about that pi bond? The electrons are held in pi orbitals. Where are those pi orbitals? Outside of our structure, which means what about their reactivity? They're more reactive than our alkanes. Okay? So in our alkenes, that pi bond is now a site of reactivity. We can take those electrons and do something with them. Okay? So our double bond is a source of electrons. What things are sources of electrons?
Bronsted.
Okay. Absolutely. Bronsted, yes, that's part of it. We could look at it as a Bronsted
Base.
a Bronsted base. It can donate those electrons to a hydrogen ion. What else could we do with those electrons? Does it have to go to a hydrogen? No. It could go to any other positively charged atom. If it goes to another positively charged atom, what are we looking at? We've got a Lewis base, or potentially a nucleophile. Okay? Now that we know something about its reactivity, we can start to predict what's going to happen with these. Which of those chemistries should we evaluate first? Which of those chemistries is, quote unquote, the easiest chemistry that you've seen multiple times before? Your Bronsted-Lowry acid-base chemistry. So that's probably going to be the best place to start because that's the one, in theory, we're most familiar with. So we'll look at the reactivity of our Bronsted-Lowry bases first. Okay? So there's a nice little summary there. I know I was supposed to have pictures in there. Give me a break. Okay? So our pi bond is more reactive than our sigma bond due to its location. Okay? Again, remember if we looked, if we look at where our pi system is, go back to our carbons, our pi electrons are held outside. Here are your sigma electrons inside, and your pi electrons are out here. So your pi electrons are further away from the atoms. That makes them much more reactive, more accessible to the local environment. We could potentially have them interact with something else. As a source of electrons, can act as a Bronsted base, Lewis base, and nucleophile. Okay, so let's pick the easiest case. Let's take a look at ethylene with an acid. How do you know HBr is an acid? The answer I was actually looking for was yes, because I told you so. So good job. So we've got ethylene and HBr. If we're going to look at or try and let the chemistry solve the problem for us, we could go through and run a face test. Which of those would you be a little bit more nervous about being splashed in your face? HBr, because it's a strong acid. What part of HBr concerns you? The hydrogen. What charge on the hydrogen? Positive. What do we need to find in the other structure? A negative. Where do we have electrons? In the pi bond. So what we could do, if we're going to now try and show the motion of electrons, so this is now a mechanism, we're going to show the electrons from that pi bond moving towards that positive hydrogen. Okay? If we've now shared electrons with that hydrogen, what have we formed? a bond. How many bonds would we have around that hydrogen now? 2. Can we have 2 bonds? Nope. So what do we have to do? We have to break a bond. Which bond do we break? We'll break the hydrogen-bromine bond. Where should those electrons go? Why should they go to the bromine? Because it's more electronegative than hydrogen. Okay? We've now shown what we want to try and show, so let's go ahead and see what happens, or our result from this. We didn't do anything to our carbon-hydrogen bonds. We didn't do anything to the sigma bond between those 2 carbons. Okay, I'm going to draw on the bromide first before we start looking at the hydrogen. Okay, the bromide gained electrons, started neutral, gains electrons, which means it is now negatively charged. Where does that hydrogen go? Okay, to the carbon. Which carbon? Doesn't matter in this case. Okay, so let's go ahead and say, oops, sorry, make that a hydrogen. Let's go ahead and draw on that hydrogen, and I'm going to color it so that we know it came in there. Right here. There's our hydrogen. Happy little hydrogen. Are we done? No. What's wrong with this? Our carbon's not happy. So what can we do with our structure to make sure that we show that that carbon is not happy? Make it obvious. We have to make it positively charged. Why is it positively charged? Because it lost electrons. Okay? If you remember way back when we first started this chapter, when I asked you to draw out a Lewis structure, okay? The Lewis structure that I drew out to begin with looked something along these lines. So let's draw a resonance structure here. And I had this. And I said this structure was going to come in handy because it was going to tell us something about the chemistry of our compound. We've got that positive and negative on those carbons. Okay, that is a possible Lewis structure. It's a bad one, okay, because we've got charge within our structure, but it is still a possible valid Lewis structure. How can I stabilize that negative carbon? I could share those electrons with the other carbon, but now let's say we bring in HBr. HBr is what kind of an acid? Which means dissociates completely into the ions. What are the ions? H plus, Br minus. How do I stabilize the negative on this carbon? Let's give it the hydrogen. How can I stabilize the positive on this carbon? I give it the bromine. Okay, so I could end up with this as a possible answer, knowing really nothing much about the mechanism. Well, let's go back to our mechanism. We've got that positive charge floating up there, which kind of makes sense, because if we look at our structure that we drew down below, if we put our electrons on that rightmost carbon, what happens to the leftmost carbon? It has to be positive. Okay, so now let's evaluate our materials up here at the top. Is carbon happy as a positive charge? No. So what do we need to do to fix that? We need to give it electrons. Do we have electrons? Do we have, say, a bromide ion with electrons? So what could we do? Let's take those electrons and let's share them with that positively charged carbon. What's the result? Carbon was positive, just gained electrons, so it's become neutral. Our bromine was negative, lost electrons, so it's now neutral. And we have now a happy final product. Let's compare our final product that followed our mechanism and looked at exactly in detail where all the electrons moved to we had no clue what was going on except we had positives and negatives and we just paired them up. What's the difference between those two answers? Absolutely nothing. A heck of a lot less work. Okay? So understanding something about the resonance structures and where you have charges starting to build up, you can start to predict your products without understanding anything about the actual chemistry behind them. What if I instead did not HBr, but now let's mess with this. I don't want to do HBr, I'm going to do HCl. What's the product now? Same thing, except instead of bromine, it's chlorine. Okay? What if I changed it to recording? That's not a good thing. Actually, I don't want to change it. We're going to stick with that for the moment. Okay? So all we're trying to do is find those positives and negatives and force it to react. Okay? So let's make it a little bit more difficult, because everybody likes things more difficult, right?
Sure.
Why not? Yes.
So the one that had the carbon-carbon with a positive and negative charge on the bottom.
Yes.
On the side, is a resonance form? Or is it just
Yeah, give me a sec here.
it's just an unstable resonance form?
So if I ask you to draw out the Lewis structure for propylene, we would get C3H6. You could draw this out. To do that, how many carbons are there? 3. How many electrons does a carbon bring in?
4.
How many electrons does a hydrogen bring in? 1. How many hydrogens are there? Total electron count is?
18.
So what we can go through and do is now draw a Lewis structure and put in our carbon backbone. Because I know the answer, yes, I can arrange this a whole lot faster than you would be able to. As far as our electron count goes, 2, 4, 6, 8, 10, 12, 14, 16. I'm missing 2 electrons. If we go back through and evaluate octet rules, does this carbon have its octet satisfied? Yes. How about this carbon? No. So how could we satisfy that? Let's give it those 2 electrons. So there we go, that octet's satisfied. How about that carbon? No. How do we fix that? We could share those electrons across. Let's say instead of sharing, we said, screw you, carbon. I'm just going to leave you as is. What would we have to do to our structure? This carbon is a positive charge. This carbon is negatively charged. Okay? And we go, oh, shoot, that was a really bad idea because I now have charge in my Lewis structure. So instead of saying, okay, I don't like you, carbon, I'm going to have to say, okay, I'm going to give you electrons. So what we could do is now show the sharing of electrons into that bond, and what we would end up drawing would be this. What changed between those 2 structures? The location of electrons, and that was it. Which means, what's the relationship between those 2 structures? They are technically resonance. Okay? The one that's got the red bonds, yeah, you're right. That is a bad resonance structure because we have charge. Okay? Why do we want to look at it? Because that shows us something about the chemistry. Okay? It's a little bit more helpful to look at that. Okay? So if we try and run this reaction again, now with HBr, same deal, what's going to happen in our first step? Okay, we're going to take the electrons from that double bond. We'll share it with the hydrogen. Electrons go to the bromine, right? There's a reason I'm drawing up here in a second. Yes?
Would it suggest that the hydrogen and bromine is already associated?
Technically, yeah. You would, and that's why you'll see me show H plus a lot, because I'm saying we're adding a strong acid. Whoa. Okay. Where should I put that hydrogen? On the 2 hydrogen? Okay. So let me draw that hydrogen. Raw! Rage! Delete everything. Terrible.
I really felt it when you said rage. It was a great word.
Are you mocking me?
I would not mock you in such rage.
Okay, you guys are going to have to remember I've already drawn that first part, so I'm not drawing it again. We said you could put the hydrogen on the second carbon. I think I'm going to have to draw it again. So we could draw it here. How many of you think we had to draw it on the second carbon? What's that?
I meant where the 2 hydrogens are.
I like that. Let's take a look at that. We will be stopping here with this, just so you know. Let's add it there. Is our structure finished yet? What do we need to add?
Charges.
Let's not do the bromine yet. All we did was it react with hydrogen. Let's put our charges in. Where are our charges? In that first structure there on the last carbon. In our second structure, our bottom structure, it's on the middle carbon. If we then did the reaction with bromine, the bromine either ends up on the last carbon or the middle carbon. Those of you really good with nomenclature, that top one would produce what as far as a name? Bromo propane. Or if we want to get specific, that bromine would be attached to carbon number 1. If we looked at the second one and we pushed that out to its product, we'd still end up with bromopropane. Where would that prane, what the heck is that? Propane. It would be 2-bromopropane. Do we end up with the same product? No. What does that mean? One of these is right, one of these is wrong. That's what we'll pick up with on Tuesday. Cliffhanger. Okay? What you need to evaluate is the difference in those intermediates. Look at the carbocation. Try and classify and rank that carbocation. Give it a name. We have given you, or I have talked about how you should be able to finish this problem off. You should be able to answer it.